That's a good question. I'm one of the many engineering experts at ON Semiconductor, and I have the answer for you. Driving the LEDs in a low-cost light bulb can be as simple as a circuit below, where a single constant current regulator, or CCR, is placed in series with an LED or a string of LEDs. This circuit is low cost and simple. However, it is not very efficient, around 64%. The power factor, PF, is 0.97, which is very good, and a total harmonic distortion, THD, around 21%, which is pretty decent. The LED could be a string of LEDs or a single LED with a forward voltage of 100 volts. For example, 5 20-volt LEDs or 30 3.3-volt LEDs. Power companies would ideally like a power factor of 1 and a THD of 0. This is achieved with an incandescent light bulb, and as they are only 5% efficient, this is beneficial to the power company, as there's a lot of power used to achieve minimal light output. To achieve perfect PF and THD, the current drawn by a light bulb needs to follow the supplied voltage waveform, as shown below. The current in the above circuit is a step function being controlled by the CCR. When the voltage out of the bridge is greater than the forward voltage of the LED, in this example, greater than 100 volts, there is a lot of power lost as the voltage rises to 170 volts peak above the regulated current. This circuit can be modified to improve the efficiency by splitting the LED string into two stages by adding a few discrete devices. The circuit works to improve efficiency by dynamically changing the LED forward voltage to follow the bridge output. In the example below, there are two LED strings, each string comprising of three 20-volt LEDs, given a forward voltage of each string of 60 volts. Two resistors, R1 and R2, form a voltage divider and are placed across the bridge output. They are selected to switch on Q1 when the bridge output reaches 110 volts. Below 110 volts, Q1 is off and the two LED strings are now driven in parallel. When Q1 turns on, the LEDs are configured to operate in series. The current waveform now has a step function which is a little closer to the voltage waveform, and the efficiency has improved to 75%. In the reference design note, the discrete components were changed and another resistor voltage divider was added, raising the efficiency to 79%. This circuit is very similar to that above. When the bridge voltage is below 110 volts, the LED strings are operated in parallel and then being reconfigured in series when above 110 volts. The second switch, Q2, turns on above 120 volts and adds CCR2, causing the peak of the total current waveform to follow the voltage waveform closer. This circuit has a power factor of 0.99, a THD of 12%, and an efficiency of 79%. The reference design note takes this concept one step further by dividing the LEDs into 4 strings with an equivalent forward voltage for each string of about 36 volts. The LEDs operate all in parallel when the bridge voltage is below 72 volts. Above 72 volts and below 145 volts, the LEDs are in 2x2 matrix, which is essentially 2 strings of LEDs in parallel, and above 145 volts, the LEDs are all now in series. The circuit has a power factor of 99, a THD of 13%, and an efficiency of 82%. Keep those questions coming. That's what we're here for, to help you solve your LED driver challenges. Thanks for the question. Have a great day.